This is a video series I'm starting where I explain basic physics concepts from the point of view of computer simulations. The motivation for this goes back a few years. When I was taking one of my undergraduate physics college courses, I was given some reading about maximum efficiency of wind turbines. And when I was reading it, I realized that my understanding of fluids was severely lacking. The paper used all sorts of assumptions, like how the pressure in the air far away from the turbine in both directions should be the same, despite the wind being different speeds, stuff like that. Not understanding what assumptions were and were not valid was hampering my ability to keep up with a fairly straightforward calculation. But it wasn't just fluids. I wouldn't have admitted it, but at the time I didn't really get the concept of energy fully, especially how all the different equations for different kinds of energy, like how they worked and how they could all be supposedly transferred back and forth between each other. It all seemed weird and arbitrary and like it couldn't possibly be true. However, that is not to say that I was hopelessly confused or anything. I had a solid understanding of linear and rotational motion because I had written a bunch of physics simulations back in high school. That kind of direct, tangible, and graphical way of learning made a lot of sense to me in ways that clever symbol pushing just didn't. And that's what these videos are going to be about. They're not going to teach you how to do your physics homework assignments. Honestly, it's probably not even really going to teach you physics. These videos are to teach concepts to people like I was back in high school or college. Well, maybe not every video. I probably wouldn't have needed this particular video at any point, but you had to start somewhere, right? But I think that's enough preamble. Let's just get into it. So first, a warning. I'm going to be making some claims about the nature of the universe that are, strictly speaking, not true. I'm about to describe the simulation that we're going to be working with and claiming that this is exactly how the world works. It's not, but it is a good enough approximation for us at the moment. I'm going to be leaving some things out. This is for simplicity's sake. We will be adding missing things in as they come up. So with all that out of the way, let us start. Okay. So the universe operates on rules. Okay. These rules are unbreakable. These rules are known, and they can be written down as a fairly simple loop of instructions. This is it right here. Here it is, and here's how it works. First off, there's this thing called time. Okay? This is a quantity that every time this loop reaches the bottom, it increments by a constant value. Now, in the real universe, this time step is absurdly small, many billionths of a second, but that's not very useful for a simulation that a computer runs. It'd just be calculating forever. So for the purposes of approximation, we're going to be setting the timestamp for our simulations to be a small but manageable number, something like 1/100th of a second or something like that. The smaller the time step, the more accurate the simulation is to reality in general. More on that at a later date. So there are also things in the universe. Right? So we have our things here. Now, what that means is a bit of a touchy subject for us at the moment. But generally, a thing is something physical in the world, like a ball or cup or something. Of course, balls and cups and things are made up of lots of little tinier things that are all kind of connected together. So things in this concept can also mean collections of things. We'll come back to this later probably, but for the moment, things are just going to be stuff like bouncy balls, heavy boxes, tables, books, things like that. I'm going to call these by various other names at different points in times, like objects or entities. So you can see here I call them objects here. Now everything in the universe has three properties associated with it. So the first is position, which is a measure of where the thing is at. For the first couple talks, we're only going to be looking at objects that move from left to right. So the position can be described using a single number, like where on the number line it is. So in this example, this blue object is to the left of this red object, so it has a more negative position, and this one has a more positive position. Right? The second thing is velocity, which is a measurement of where the thing is going. So right now, this pink object is going to the left, and it's going to turn around, and now it's going to the right. Okay. And the third is mass, which is a measure of how much effort it takes to change an object's velocity. So here, it's not completely physically accurate to do this, but I am representing the mass for now with the size of these objects. So this blue object, you can see it is smaller than this one. So this one has less mass than this one. Okay. Now, if that was all there was, the universe would be a pretty boring place. But luckily, things in the universe can influence each other. Objects can collide, they can push and pull using like gravity or magnetism. The way that objects interact is called a force. Now, I won't be talking much about the specific forces that exist for a while, but there is one important rule about forces that you need to know. Whenever two objects or two pieces of matter interact, they always do so by exerting forces on each other. And those forces are always equal and opposite. Okay? So these concepts come together in this loop. So let's go through it. So here at the beginning, before we start, we're going to be setting our constant time interval, our constant time update. We're going to be doing this loop once every like d-teeth of a second, so once every 100th of a second in our case. This is essentially going to be incrementing like the clock of this simulation over and over and over. So at each time step, at each instant, we are going to be looping over every object that exists in our simulation. So in this case, we have two objects right here. So we're going to be doing this thing twice, once for each one. And so for each object, we do 3 steps in order. The first one is we calculate all of the relevant forces that are at play. Again, we'll talk about this later, but essentially what we do is there are a number of known forces that we can measure and that we know empirically, like what they are and how they work, and we just calculate them for every object. Then step 2, we take the force that we calculated in step 1, we divide it by its mass, and then we multiply that number by this time step that we set up here. And then we take that quantity and we add it to our object's velocity. And then we take that velocity that we just calculated, that we just modified, we multiply it by our time step, and we accumulate it into position. We add it into that object's position. And we do this once for the blue object, and we do it once for the red object. And that's it. That is the simulation. That is how the universe works, right here. So you're probably wondering, why is it like this? Like, what's the deal with like dividing the force number by the mass number? The answer, perhaps unsatisfying as it is that this is just how the universe works. Those are just the rules. They've been experimentally verified by millions over the past several centuries, and this is just how it works. To quote a famous physicist, I can only tell you what it looks like. To get a little bit more comfortable, let's look at some concrete examples. Okay, so for our first example, we have this blue object that starts off traveling to the right in a positive direction, has a positive velocity. Head first into this red area, this red force field. Now, I said in the last slide that interactions between matter always happen via a force, but in this example, a force is just existing in the world. It doesn't have another object that it's exerting it with. Just don't worry about that for now. We're starting off small. It is constant and position dependent, meaning that any object that moves into the red zone will experience a constant force in the left or the negative direction. Other than that red force field, the object experiences no external forces. Okay, so first off, let's look at this first portion before the ball reaches the force field. Now, it's fairly short in this situation, so you can't really see it, but the important thing is that the ball moves to the right at a constant speed, not slowing down or speeding up when it first spawns in. So looking at the simulation loop, this should make some sense. So the velocity term only gets modified in one spot, right here. And that is the force that it's experimenting divided by its mass. If there's no force being applied, if the force is 0, then well, it'd be 0 divided by the mass, which is 0, times dt, which is still 0. So you'd be incrementing the velocity by 0. So in other words, the velocity isn't changing. If there's no forces being experienced, the velocity doesn't change. All right, so the velocity will stay constant between iterations. So in the next portion, the ball is in the force field. Okay. Notice how the ball doesn't just like reflect off the field. It penetrates into the field, slows down, stops, reverses, and only then leaves. So again, looking at the rules of the simulation, hopefully this should make sense. A force changes the object's velocity over a period of time, right? So a force of like say 5 which only change the object's velocity by a small amount each time step. So you'd have 5 divided by the object's mass times dt, but dt is like 1/100th of a second. So you're looking at something that is maybe on the order of 5/100ths of like a unit of velocity, right? So it's changing velocity at a fairly slow rate. And the velocity acts on position, again, over a period of time. Each time around, the current velocity only changes the position by a small amount, right? You're multiplying by this dt again. So forces act on position in like this weird like second order way. It has to go through velocity, and only through velocity can it affect position. So yeah, a fun little fact to note here, the ball actually leaves the force field with the exact same velocity as when it entered, just in the opposite direction. An explanation of why that will be will probably be the subject of a later video, I imagine. Another thing to note, in every simulation I present from here on out, I'm planning on giving some like sort of pseudocode down in the corner. This is part of that concreteness that I talked about earlier. We're not going to be talking about like imaginary, maybe sort of theoretical forces being applied to objects. We're going to be talking about concrete forces being applied to objects with concrete positions and velocities. So yeah, let's move on to the next example. The situation has been modified a little bit. Now there are 2 balls. The blue one from earlier, which is exactly the same as before, and now an additional red ball. So the catch is that the red ball has twice the mass of the blue ball. So notice how the red one is able to penetrate further into the force field and how it takes longer for it to exit. So the reason for this is, of course, because of the way the simulation loop is defined. So force directly influences velocity and velocity position. If the mass of the red ball is twice as large as the blue one, then the red object will accrue changes in its velocity about half as fast as the blue one, right? Because you're dividing by the mass. If the mass is twice as large, then when you divide by a number that's twice as large, you get a number that's twice as small or half as big, you know. And that's what we're seeing here. It slows down at a slower rate, and then it speeds up at a slower rate. And so it's going to stay inside this red zone longer. So moving on, In this next example, we have two balls that initially start out moving towards each other, but there's a force that acts between them, a repulsive force that wants to try to keep them apart. Think two magnets with like poles facing each other. Right? So far away, this force is present but very small, but nearby the force is much larger. There's not much I want to say about this specifically. I hope this is fairly intuitive. I'm showing this to contrast with this example. So this is the same situation. Two balls start out moving towards each other, etc. But instead of the two balls having the same mass, the red one has twice as much mass as the blue ball. So the way that this manifests is a little bit more complicated than last time. See, the red ball has so much more mass, and thus feels the effect of the repulsion so much less, that it's able to sort of just barrel into the blue ball. It's maybe not that noticeable, but if you look closely, you can kind of see the red one just kind of push its way in a way that the last one didn't. But only at first. After barreling into it, the red ball gets close enough to the blue one that the repulsion force actually becomes quite strong enough to stop the red ball and turn it around. So remember, when two objects interact via a force, which is the only way they can interact, the force is felt equally and oppositely by each object. So going back to the simulation loop, if two objects are feeling the exact same force, but the red one has twice the mass, then the red object will change its velocity by half the amount that the blue one will. That means that while the blue object's velocity changes so much that it goes from positive to negative, the red object won't for a while. It won't even accrue enough change in velocity to even turn around. So it just keeps moving forward. Don't worry if you didn't totally get that last part. The next video in the series will delve much deeper into it. The most important observation to take away is that two objects with very similar initial states who exert the exact same forces on each other can end up in very different ending states just because of the differences in mass. Okay, so that's it for the first video, I think. The first one was admittedly pretty basic, maybe even actively harmful to my goal of providing like a resource for someone like me. But being overly concrete about the fundamentals probably doesn't hurt. The next one's going to be more interesting. It's an introduction to momentum and kinetic energy from the point of view of simulations. All right, see you then.